you need an umbrella today? What about sunglasses? Actually, maybe just step outside and see how you feel. For generations, predicting the weather has been a monumental feat of physics. Thousands of supercomputers crunching the numbers to stay one step ahead of the elements. Right now, we're in the middle of what experts are calling a Raucous Revolution, a massive shift where traditional climate science is being enhanced and assisted by new AI models. And the stakes couldn't be higher. In an era of increasingly unpredictable extreme weather, getting the forecast right isn't about whether you need an umbrella for your morning commute. It's about national resilience, food security, and technological sovereignty. Welcome to the Turing Podcast. I'm Amelia Jabry, and today we're looking at how a brilliant new AI tool called FastNet, developed right here in the UK, is changing the rules in meteorology. Joining me today are Dr Scott Hosking, Mission Director for the Environmental Forecasting here at the Alan Turing Institute, and Professor Kirstine Dale, Chief AI Officer at the Met Office. Scott, Kirsten, welcome to the podcast.
Thank you.
Thank you. So hi, I'm Scott Hosking. I'm the Mission Director here at the Alan Turing Institute. I've been at the Turing for around 5 years now, and I've been heading up the FastNet model since 2023.
Wonderful. I'm Kirsten. Thanks for being here.
Oh, thank you.
Tell us a bit more about yourself.
Thank you for inviting me. I'm Kirsten Dale. I'm, as you said, the Met Office's Chief AI Officer. I'm responsible for overseeing how we embed AI across all Met Office functions. So that's through from some of our back office functions like finance or comms, right the way through to embedding AI into our deep science. So how do we forecast the weather or model climate change, which is why I'm involved with this project, developing the FastNet model.
And Kirsten, you mentioned that you are the expert. You mentioned that we are in the Raucous Revolution. And could you explain what happened at the end of 2022 that changed the forecasting landscape for the Met Office?
Okay. I have to take a bit of a step back, really, to talk about some of the context for how we forecast the weather. So the UK Met Office is the National Met Service. We forecast the weather, as also do climate change and lots of other things, but talk about today's weather forecasting. And despite what some people might think, we don't do badly. We are consistently in the top 2 weather forecasting centres in the world. 92.5% of our next day temperature forecasts are accurate within 2 degrees. But we are continually looking for ways to improve the forecast. And some of the ways that we've historically improved the forecast are by using more data. We get more data from satellites, improving the physics, so the understanding of why the atmosphere is behaving in the way that it does, and also using enhanced compute. And those 3 areas have led to the gradual improvement of forecasts. And it's what is commonly referred to as the quiet revolution. So the steady improvement in our forecasting capability. And at the end of 2022, we saw something very interesting. And it was that AI was being used to produce data-driven models for weather prediction. And at the end of 2022, there was a step change, a big leap forward in their performance. And it made the community, the meteorological community, really sit up and think, how could we start using some of these data-driven methods? How could we incorporate this into the forecast process? And that led me to call it the Raucous Revolution, because it was such a contrast to the quiet revolution also, and the incremental change. It was this big leap forward. And then it all started from then. We started developing the early version of FastNet with the Alan Turing Institute and launched our partnership. So that was the background.
So you had the Quiet Revolution and then the Raucous Revolution. Thanks for explaining that. Before we go into FastNet, we probably need a little bit of context into the traditional weather prediction models, which you've just mentioned, to AI prediction models. So, Scott, a question for you. How do traditional numerical weather prediction models, so NWP or physics-based models, differ from AI weather prediction models?
Yeah, they take a very different approach. So our physics-based models, they are built on the understanding of maths and physics, the atmosphere, and we model those maths and those equations at each grid cell on Earth, for each level through the atmosphere and across time. Now, AI models take a different approach. They learn from the past and what they've seen. So we've got 40 years of good climate data or weather data from European Centre for Medium Range Weather Forecasting, this ERA 5 dataset, which we'll say more about later. And the AI models are very good at learning patterns from lots of data and then using these patterns of what it's learned from this data and projecting it forward. But with no, on the face of it, no idea of physics. They've learned that physics through the data.
Yeah, so they've been taught to spot a pattern, but they don't know the fundamental reasoning behind that pattern.
Absolutely.
Okay, so why does physics remain important in weather forecasts? Why can't we just purely go into an AI weather forecast if they are doing well?
So I think the physics remains important for a number of reasons, but probably one of the most compelling reasons is that physics gives you the critical process understanding of why a forecast is giving you the output that it is. Because our physics models, so our numerical weather prediction, they are based on the conservation of mass, energy and momentum and the Navier-Stokes equations. These are equations that capture the physics and describe how the atmosphere is going to behave. So that deep understanding gives you trust and confidence in the forecast. So that's the first reason that it's really very important to continue to develop the physics. The second reason is that the physics models produce the training data that is then used to train the AI models. So there's a bit of a symbiotic relationship going on. With the current generation of AI models, you need the physics models in order to get the training data. And then the last point, and perhaps Scott would like to expand on this a bit, is that because the AI models are developed using the training data, they will typically only predict what they've experienced within the training data. Now, that means that there are some events which are typically called usually called Grey Swan events, which are physically plausible but statistically unlikely. Now, if those events are not within the training data, the AI models are not going to predict them. So this means there's an enduring need for the physics models.
Just to follow up on that, we know that our climate is shifting. We are year on year, our atmosphere is warming, and we're seeing more and more records being broken in terms of heat waves around the world, hurricanes, droughts being prolonged. None of these are in the training data. Every time we break a record in the world somewhere, that event is not in the training record. And so when I talked earlier about AI learning patterns, but we're introducing new patterns into the world. So that's why physics is so key to be part of that model design so that we don't accidentally miss some of these what could be catastrophic events. AI has its strengths, but the physics there really provides that trust as well in the methodology.
Yeah. I feel like we've done quite a good job to big up the physics, but I think I also need to big up the AI models. So the AI models, they may not be at the moment able to cope with the Grey Swan events or with our changing climate, but they are phenomenally fast. They're not just a little bit faster, they're tens of thousands of times faster than traditional models. And that brings with it a whole set of attributes and possibilities that it's really exciting for us to think about how we might use this in weather forecasting. One of the reasons the AI models are really fast is because they're very computationally light, which means that you could run them on edge computing. We're not there yet, but in the future, you may be able to run a weather model on your mobile phone. It also, because it is computationally light, means that you can run it very close to the time that you actually need the forecast, which means that you can integrate and use opposite ground truth data right up to the time when you actually need that, and that improves the accuracy of the forecast. And then finally, because they are computationally light, there's less of an environmental footprint, which is only true when we talk about the inference stage, not the training stage, which is still very computationally heavy. But inference is got a lighter footprint.
Okay, so yeah, very compelling reasons why both at least now need to exist and why one actually assists the other, that physics-based models can help inform the gaps in AI models, but AI models seem a lot faster. And before we dive in further into FastNet, Scott, from the Turing's perspective, why is this specific partnership with the Met Office so vital for the UK?
So the partnership with the Met Office is crucial. Let's just look in the last 6 weeks. This is our third heat wave, I think, this summer already. And we've seen hospitals and schools struggling with the heat, how to keep patients cool. There have been kids at home from school because it's so hot. My kids had to come home early that day. We've seen spikes in energy costs in the UK, importing more from Europe. We also need to make sure that we're not stepping or moving towards droughts, hosepipe bans, all these things we need to keep an eye on. The government needs to have that information in a timely fashion to make sure we can keep people safe.
Scott, can I build on that? I think that you've really nicely highlighted why I think the partnership's so valuable, because it really brings together these cross disciplines. It's this multidisciplinary team of data scientists and operational meteorologists and physicists, and together we're really making the model as good as we can possibly make it to support a step change in weather forecasting. And I know, I've worked at the Met Office for a long time. I know why the weather's important, but why is the weather important to Turing?
That's a really good question. I'll take an example. If you look at the World Economic Forum, every year they produce a report which tracks the global risks in terms of severity. Now, in this year, I think the report came out in January. What tops the list in terms of risk over the next 10 years is extreme weather. And it's up there against misinformation and disinformation, cybersecurity, the adverse effects and outcomes of AI models. And all these things we hear in the news daily, but extreme weather is right at the top of the list. It's one of the key global concerns in the next 10 years because it costs governments billions, tens of billions in damages when we see flooding events, when we have heat waves, and it affects people's lives and health. So absolutely it should be up the list. And that's exactly why Turing is focusing on it.
Yeah, absolutely. It's a very intersectional problem. We had a previous episode where we talked about critical national infrastructure, things like our water systems and our hospitals, etc. And these are greatly affected by weather. And as you said, the more information we have, the better. And it is cutting edge weather models that can give us this information. So let's talk more about FastNet itself.
Yeah, before we go any further, we should explain to our listeners why we've called this FastNet. So FastNet is a nod to the shipping forecast. Maybe this is one for Kirstine.
Yes, you're absolutely right. It is a nod to the shipping, to all in the shipping zones. And it's also to our founder, Vice Admiral Fitzroy, who started the Met Office and also initiated the shipping forecast.
For non-experts like me, how does an AI weather forecast, i.e. mesh passing between nodes, differ from the AI that we see in LLMs like ChatGPT?
So often when we talk about AI, everyone assumes AI is large language models, LLMs, ChatGPT and Claude, and this is what AI is. But what we're developing here is also AI, but a very different type of AI. So large language models, you can think of them as sentence completers and be able to predict the next word or the next few words based on what it's seen up to date. The models that we're developing, such as FastNet, completely different beast. These are digital twins of the Earth, trying to learn the spatial, temporal patterns right across the globe, really trying to learn that context and trying to learn that physics through seeing lots and lots of data. And there's the complexity in terms of the meshes, which we can get onto in a moment, and that information is another level. So yeah, on the geometry and these meshes, so FastNet uses a icosahedral mesh to map the Earth. So Kirstine, can you say what that is?
Okay, now you've given me the one with the tricky word to say, icosahedral. Okay, I think it's probably easiest to think. If you think about historically, numerical weather prediction models have used the lat-long grid of the Earth, and because of that, because those grid boxes get smaller at the poles, you get more data per grid box when you use the lat-long grid. It's a bit
Lat-long
like
being latitude and longitude.
Yes, that's exactly right. Yeah. So it's a bit like when you try and, I've done this many times because I've got a son, when you try and wrap a football at Christmas, you'll end up getting lots and lots of paper at each of the top and the bottom. That's the same for weather modelling. You end up with many more data points at the poles, which is not the even distribution you want. So to get round that, in the FastNet model, we use a icosahedral mesh, which is like a 20-faced die. And that gives a more even distribution of the data points, which it supports better modelling, really.
I really like the sort of 20-sided dice analogy. So this is a podcast, so we don't have visuals here.
Yeah.
I normally have my PowerPoint ready, but not in this medium. It doesn't really work. But 20-sided dice, so that's 30 edges and 12 vertices or 5 points, 12 points. And you can think of these vertices as the nodes in your graph neural network, and information is being passed across these nodes in the connections between nodes in your 20-sided dice. But we don't just stop at a 20-sided dice. We get finer and finer in resolution. So we add up to over 40,000 nodes in our most finest mesh, which covers the planet. And we're passing information not just within each mesh between nodes, but also across those different mesh or different hierarchies of granularity.
It's amazing to think about when you're looking at weather prediction. You're thinking about how, I guess it's pretty simple to imagine there's a pattern of weather that has existed before and that an AI might predict what happens next by pattern recognition. But to actually have a conception of the shape of the Earth and how the geometry plays into it is a tricky problem I had never thought about before, but it makes so much sense when you use the analogy of the dice or wrapping the ball especially, and you've got all the bits of sticky tape right at the poles.
It'd be a lot simpler if the world was just a perfect square.
Yeah, I think
Or
a lot
if
of
it were
things.
flat. If it were flat, that would help a lot.
It would really make the modelling so much easier.
I want to maybe point out to listeners that we do think the Earth is round. From this, so we've talked about the geometry, and now we're on to the data. You trained FastNet on 40 years of Era 5 data. Kirsten touched upon the existence of these worrying Grey Swan events earlier. What does the AI, in quotes, see in 40 years of weather, and what a human or a physics equation might miss?
Yeah, 40 years is really the blink of an eye in terms of our climate history. Our Earth has been here for something like 4.3 billion years, and we've just got the weather and an estimate of weather at that for the last 40 years, because we don't have sensors on every square kilometre on Earth.
Yeah, tricky.
Let's think about the current context, 2026. We're about to see a Super El Niño. We see one brewing in the Pacific Ocean right now. Now, seems to be the biggest we've had since 1877, 1878, where we saw global famine killing over 50 million people, or 3-4% of the world's population at the time. There's no way that something of that magnitude appears in our 40-year record. It's a huge event. And El Nino events, this is a change in the sea surface temperatures in the Pacific Ocean, and that really sets up a change in the convection and the atmospheric circulation right around the world. So we are going to see areas which are wetter become drier, and regions that are dry become wetter, because we see shifting patterns. I'd be really interested to see how our AI models cope with such a big change.
Thank you for explaining what a Super El Nino was as well, because it's been a while since I did A-level geography. You mentioned these Grey Swan events, Kirsten, which you said were physically plausible but statistically unlikely events, like we've just mentioned the Super El Nino. So this sounds quite worrying. So how do we train an AI model to predict extreme weather events, things that have never happened before, if the model only knows what has happened in the past?
Extreme events are often on the front of people's minds, and how we manage and you prepare for those events. Now, those events are hard to predict because we haven't seen them in the training data, and often we call them tail events. So if you think of a distribution of events, these extreme events are near the tail, where we don't have lots of examples of those. So uncertainty is absolutely key. So being able to run hundreds, thousands, even tens of thousands of future scenarios with our model, future runs, really helps us stress test our infrastructure and the services to the whole range of potential outcomes. AI for weather forecasting is still in its infancy. We've only been developing these models for a matter of years. There's still a lot of work to do. At the moment, we have AI weather models and this huge decades of research in physics-based modeling. And I think the challenge now is how we start working with them both and bringing them together and working out what the right blend is of the two.
Yeah, they seem to have a lot of potential, and so I'm excited to see how it's developing. Talking of the development, what other weather models are there at the moment, and how do they compare to FastNet?
I think the key thing to observe at the moment is that The current version of FastNet is a global model. So there's lots of comparators. There's the AIFS model produced by ECMWF, GraphCast, and
Pangu
weather. I think last time I counted them, there was about 20 different weather models. So there are lots of models. But I think the really exciting thing for us is that we're about to come to the next version of FastNet that I'm sure Scott would like to hear more about, which is going to be a regional model for the UK.
Yeah, we developed FastNet, and in terms of model skill, root mean square error, we're in the pack. We're as good as the others. And we could have kept pushing to try to get further and nudge ourselves up the list. But actually, let's play a different game here. We've got access to amazing data working with yourselves in the Met Office. We have this 10-kilometer global data set that FastNet will have access to, but also this UKV 1.5-kilometer data set for really high detail for what's happened in the UK, and we can train a model on that. I feel like that's changing the game. Let's not try to catch up and compete with the big tech. You have bottomless pockets and able to big compute, and there's only so much compute you can throw at a problem when you start realizing, actually, my data doesn't have the information or the patterns that we talked about. So we need good data. And models can only be as good as the data that we put into them. No one else is training a AI weather model for the UK at this resolution. When we come to version 2 of FastNet, we're going to be, we can't put ourselves up on a chart against all the other models because we're the only ones doing that. And the other aspect here is we're working with the Met Office and a deep domain expertise of physicists and meteorologists in the building. So we want to make sure that every design decision is based in physics and not just some metric and that we're trying to capture. So we're working with operational meteorologists. When they've looked at our forecasts, they could say, that looks realistic, or no, it doesn't. Yes, it might score well on some global metric, but it doesn't look sensible. It doesn't look physically realistic. And that's important for trust if we're going to develop something that ultimately will become operational.
I really like that answer, and the eternal quote, the model is only as good as the data that feeds into it. And so we know that FastNet represents a step change in efficiency compared to traditional models, which we've just discussed. So, for example, a 10-day forecast can take just a couple of minutes to generate on a single GPU compared to 40 minutes on a numerical weather prediction model running on thousands of CPUs. But does that come at the cost of accuracy, or are we reaching a point where this is negligible?
So our paper has just come out, version 1 of FastNet, which is the global model. It's a deterministic model at the moment. We're building ensembles and that's coming later. But what we did in this paper is modify the loss function really to make sure that we're addressing some key challenges and problems that we've seen in AI models to date. So this is a lot of the AI weather models, we see this blurring. And what happens here is that as the model tries to reduce its error, what it does, it just blurs out the signal rather than having confidence and creating nice sharp edges and features. It'll just start to blur things out because that's the way that the model reduces its error, by just hedging its bets.
Okay, so it's more pixelated to give a visual.
Yeah. And we don't get that sharp structure that you'll need for a front of a storm or a weather front. Mm-hmm. Another thing that we're also addressing here is what's known as the slow wind bias. So trying to make sure that models both capture the wind speed and wind direction. So it's well known that models will reduce the wind speed to compensate for the direction of wind errors. So one thing we've also looked at in our model is to make sure that it gets that, because wind speed is absolutely key if you're interested in extreme events. And again, if you want something that is trusted and is useful and operational at the local level, then we need to make sure we're addressing those things. And the other are these forecast artifacts, which actually, if you look at some of the details of these AI weather models, and I'm not just talking about our original FastNet before we introduce this modification of the loss function, but you start to see the underlying mesh appear in the output. So we talked about this icosahedral mesh earlier. Did I say right?
Icosahedral, yeah.
And so in some of the horizontal wind variables, see this hexagonal honeycomb-like structure appearing in the output. And this is undesirable. This is not physically realistic.
That's
so
not
again,
what wind looks like.
It's not what wind looks like. And if you show it to someone who knows about weather, they'll go, "What is happening here?" And it's their AI model and that mesh appearing in the output. So that's another thing we've addressed. And you'll see in our paper that actually we've limited and reduced a lot of this, and now it looks far more sensible, physically realistic, and therefore more trustworthy to use for in time when it becomes operational.
I think that we need to consider the two costs of FastNet. So it's light at the inference stage when you're running the forecast, but it's still computationally quite heavy at the training stage. So when you're training these models, it's still a significant compute cost, environmental cost, and that has to be borne in and considered as one of the trade-offs when you're thinking about running an AI model.
So there's a lot to factor in, and not just if we can make it as computationally efficient as possible.
Yeah, so Kirsten mentioned these are super fast and we can run on compute. So, even compute that a computer that fits in your hand. Seen these, NVIDIA have this DGX Spark, which we've got some in the other room here. But the thing is, you need the infrastructure. You need to be able to feed the model at inference time. And we also then, the output of that model needs to go somewhere. So yes, they might be light, but they still need that long sort of supply chain of gathering the data through to the pre-processing, running the model, and then how we provide that to operational forecasters and then the general public.
I think there's another point that we need to make here in that when you traditionally might talk about this as green AI, but the greenest AI is going to be no AI. So what we're really talking about is environmentally responsible AI and about making a decision about where it's appropriate, where the trade-offs are appropriate to use an AI approach. And that may well be the way for AI and weather forecasting in the future. We may well be approaching a stage where actually running these local models, it could be done in a light computational way that supports environmentally responsible AI. This collaboration between the Met Office and Turing has been a real blueprint for pulling together different disciplines, for pulling together the data scientists with physicists, with meteorologists, with people who really specialise in what is the impact of the weather going to be once it happens. And working across those disciplines is enabling us to move forward with a better forecast that is more meaningful and delivers more value for the people who actually need to make day-to-day decisions. We really need all hands to the deck for using AI to tackle some of the big societal challenges facing us today. And we don't really have a very diverse workforce. I'm just going to use gender as one aspect, but in all aspects, it's not as diverse as it should be, the AI workforce. So, for example, for gender, I think it's 1 in 5 are women working in data science, which really isn't good enough. And why do you need a workforce to be diverse? I think it was Professor Dame Wendy Hall said, if it's not diverse, it's not ethical, which I completely subscribe to. But if that weren't enough, a diverse workforce is also more resilient, it's more productive, it's been proven to deliver better finances for an organisation. And the thing that is really the killer is a diverse workforce is more innovative, and we've never needed innovation as much as we do at the moment. AI, I truly believe, has the potential to help us address these big societal challenges, but only if we have the catalysts of a diverse workforce, so we get the innovation that we need.
Yeah, absolutely. This is a critical and urgent problem that we're talking about, and climate science and, if anything, climate justice is very intersectional. And so it's great that you're highlighting this, and hopefully if you're listening, we'll tell you where to find out more about these projects as well. So we're talking about this cross-collaboration, but then we're also talking about sovereignty, because why is it important for the UK to have its own AI weather model like FastNet, rather than potentially relying on big tech companies in the US or Europe?
This is a really important question right now. So Access was withdrawn from Anthropic's best model that was just released a few weeks ago. And we can't be in a position where we talked about the importance of weather forecasting for the UK, for the services we rely on, water security, food, retail, people's lives, schools and hospitals. We can't put all that in the hands of foreign companies when it's so crucial to our daily lives. So we need to make sure we own the supply chain, from collecting of the data, piping that data through to models, being able to run our own models, having the skills in the UK and developing the workforce that understands and that can adapt these models, and then being able to explain how these models, to make sure that they're not just black boxes, that we actually know what's happening under the hood, and we can develop decisions from that.
I think I would also add there, I mean, yes, I agree, Scott, but there's also an element of science it's down to we need international collaboration. So we really need partnership. Weather and climate don't respect national boundaries. So this is a very strong case in point that we need the international collaboration.
Yeah, I completely agree. We want to see these capabilities in all countries, and the diversity is so important as well. We're not going to get it. We're not going to have all the answers in our AI weather modeling. There's going to be strengths of different approaches, and that diversity across the world is so important as well.
Yeah. I really like the phrase that you just said, which was weather and climate doesn't respect national boundaries. And I think that kind of in one sentence summarizes everything we've said about diversity and sovereignty and collaboration. And from that, we are now looking towards the future and the potentials of FastNet. Will the insights from FastNet start influencing the daily forecast we see on our phones or other uses such as agriculture and emergency planning?
I think this is the way we're going in the future. So ultimately, yes, this is a really exciting piece of research that we're doing together in developing this model. But ultimately, the value of the model is going to be in how we use it and the decisions that it informs. So this is part of the future for FastNet. One of the aspects that I'm particularly excited about is we're thinking about developing an ensemble version of FastNet. This will really help us understand uncertainty in the model and come up with a more probabilistic version of a weather forecast that helps people mitigate risk, but also looking at developing the next version of FastNet, which would be a regional model.
Yeah, so training our model for the UK at 1.5 kilometer resolution, the detail. I'm really excited to start showing those animations. The detail we're going to see in those forecasts is mind-boggling. There's a lot of data points in that model, but it's going to provide the detail we need for the whole of the UK. The forecasts are going to be something we haven't seen in AI weather modeling before. So that's version 2. Very excited about that.
I personally, doing videos for the Turing, love a good animation. Whack that up on the big screen. From improved UK sovereignty to meshes that map the geometry of our planet, tools like FastNet are proving that the future of weather forecasting isn't just faster, it may be smarter, greener, more diverse, and uniquely tailored to keep us resilient in an unpredictable world. A huge thank you to Kirsten and Scott for joining me today and helping us see through the storm.
Thank you for inviting us.
Thank you so much.
Yeah, it was great. Where can listeners learn more about what you're doing?
Oh my goodness, we're everywhere. Definitely keep an eye on our website, keep an eye on the blogs, keep an eye on LinkedIn. As soon as we get more of these exciting results, we'll be publishing them widely.
Yeah, absolutely. Follow us on LinkedIn, and in the show notes, we can include some links to the web pages, the blog, the paper that's just coming out as well.
Yeah, we will do. So check our show notes. And of course, thank you, the listener, for listening. If you enjoyed this episode, make sure to subscribe, leave us a review, and share it with someone who's curious about where AI is taking us next.